In this video, I'm going to finish off 6.1 by doing a couple more examples. So the first one is going to be the series, the sum from 0 to infinity of n factorial times x to the n. And we're using the ratio test to determine convergence. Right, so we have rho is equals to the limit as n approaches infinity of an plus 1 all over an. Right, remember our an here is n factorial times x to the n, and an plus 1 is n plus 1 factorial x to the n plus first power. So we plug all of that into here. So that's gonna be, oops, I made that a little too long. An plus 1 is n plus 1 factorial times x to the n plus 1, and then an is n factorial times x to the n. And so, right, we can rewrite, remember, n plus 1 factorial, that's the product of the first n plus 1 terms, which is equivalent to the product of the first n terms times the n plus first term. And then x to the n plus 1, we're able to rewrite using rules of exponents. So that gives us the limit as n approaches infinity of absolute value of n factorial times n plus 1 times x to the n times x all over n factorial times x to the n. And since all of this in the numerator is multiplied, we can divide it out by the same things in the denominator. Right, so then all we're left with is the limit as n approaches infinity of n plus 1 times x. Right, and we know that n plus 1 is positive, so that doesn't need absolute value, and the x is not changing because what we're changing is the n, right? The limit as n goes to infinity, right? Not 1. Right, so then you see that this limit here, right, is, if n is going to infinity, then infinity plus 1 is infinity, right? This whole limit is going to infinity. So rho is equals to infinity. And remember from the ratio test, so therefore, by the ratio test, the series, right, the sum from 0 to infinity of n factorial x to the n diverges for all x not equal to 0. Right, so remember that from the ratio test we had 3 possibilities, and one of them was that if your rho ends up being infinity, or if rho is greater than 1, then we get diverging. So the only place this would converge is at its center, right? When x is 0, there's, right, the center is 0. Right. So the series only converges at x equals 0, its center. Right, so the radius of convergence. Right, so I'm moving from the center. That's the only place where it's going to converge. And why is that? Remember, why is that? Is because at the center is when x is 0. So if x is 0, then all of these terms are going to be literally 0, because it's going to be 0 times whatever this is, but that 0 times anything is 0. So then we're just summing up 0 infinite number of times. So we see that it converges only at x equals 0. Okay. So remember, for our three options of power series, right, it's either the series only converges at the center. So for power series, we had three options. And the first one was that series only converges at its center, which remember is x equals a, and diverges for anything else, right? And in that case, r is equal to 0. There's no radius of convergence. The only place it's going to be at the center. And then the other one is that the series converges for all x. And then the third is that the series converges for interval of convergence. Okay, so let's do one more example. So B, we're doing the sum from 0 to infinity of x minus 2 to the n all over n plus 1 times 3 to the n. Right, so we need to check convergence. Again, these have exponentials, so I'm going to use the handy dandy ratio test. And so right here, we know, right, to get an plus 1, all we have to do is replace n with n plus 1. So I'm going to do that everywhere. So n plus 1 plus 1, that's going to be n plus 2. Then 3 to the n plus 1. And in the denominator, we have the original an, n plus 1 to times 3 to the n. Oops, I dropped my limit sign. Right, and now we're gonna keep change flip. That was our first simplifying step. Right, so we're gonna keep the numerator the same, so that whole fraction that's in the numerator. And then we're gonna multiply by the reciprocal of the denominator. So I'm gonna bring the bottom's denominator up. Okay. So this is where we are, and now we're gonna start rewriting things, right? So we know that, I'm gonna just come down here. So we know that we can use rules of x. Let me actually bring this a little bit over. We know that we can use the rules of exponents to expand x minus 2 to the n plus 1 into 2. N plus 1 is just going to stay the same, and so is 3 to the n. Then we have n plus 2. Did I? Okay, no. And then 3 to the n plus 1, we can split that as 3 to the n times 3. Then we still have this x minus 2 to the n that we bring down. Right, so what's in common we can divide out. So we can divide out those and the 3 to the n. Okay, so then what's left? Right, in the numerator we have x minus 2 times n plus 1. Then denominator we have 3 times n plus 2. Right, and then now remember that, like, we can take out the x stuff because the limit is not on x, the limit is on n. So I'm going to take out the non-x stuff from the numerator and the denominator. Right, and then what's left is n plus 1 over n plus 2. And remember, if the power of the variable is the same, like here, it's just power of n to the power of 1 on both, right? We use the coefficients, so that limit, this limit is just equals to 1 over 1. or 1. Right, so our rho is equals to x minus 2 over 3. So this is our rho. So remember, for the ratio test, we get convergence if rho is less than 1. So recall that the ratio test says if rho is less than 1, the series converges. So basically, since rho depends on x, right, there's an x in there, we got to see for what x is rho less than 1, right? So we need to check what x values make rho less than 1. So our rho, which is x, absolute value of x minus 2 all over 3, we want that to be less than 1. So let's solve this inequality. All right, so I'm going to multiply both sides by 3. And then remember, if you want to take off absolute value signs of this inequality, you need to make a sandwich. Right now I can add 2 to all sides. So remember, whatever you do to one side, you got to do to the other side. So this right here is where the series converges. But remember, right, we don't know right, like we don't know if this works for, so what about at x equals -1 and at x equals 5. So remember that we have to check this, because remember when we stated the power series, when we stated the statement, we said that the series converges if x minus a is less than r, and when it's equal to r, right, it may converge or diverge. So we have to check that. It doesn't give us a guarantee, right? So on our example here, this is our, right, this is our x minus a less than r. So we already know the radius of convergence, r, is 3 in this case, and we knew just from looking at this, right, remember the center is what's being subtracted from your x, so our center we know is x equals 2, which makes sense because that is what a is. So center is x equals 2. Okay, so now we just have to check those endpoints. So basically what we do is, right, we take, right, so basically why is this happening? Remember, like, why we have to check this is because, right, so we don't know if it converges or diverges at x equals -1 and at x equals 5, because the ratio test is inconclusive at rho equals 1. And what does that mean, right? That means that we couldn't just add an equal sign to all of this, right? Adding that equal sign, we don't know if we can add it yet because the ratio test is inconclusive for that part. So now we need to use another test, another convergence test, to check if the series converges at x equals -1 and at x equals 5, right? So let's take our series, which was way up here, and now we need to, plug in x equals -1, right? Then we would get, right, the series, the sum from 0 to infinity, right? X is now -1 minus 2 to the n all over n plus 1 times 3n. So now let's simplify this stuff, right? So -1 minus 2 is -3. So that's -3 to the n all over n plus 1 times 3n. Right, and we can split this up so that way we can simplify it into two fractions, right? So we have -3 to the n over 3n times 1 over n plus 1. Right, so right now I'm just simplifying before I even use a convergence test to see what kind of series I'm really dealing with. So remember, if you have stuff raised to the same power, you can actually take that out. That's one of the exponent rules. And so -3 divided by 3, now that becomes -1. So I actually am dealing with an alternating series, right? So this is an alternating series, right? So for the alternating series, remember, we take out the -1 part, so we're looking at just the other part, which in this case is 1 over n plus 1, and we know that that's decreasing, right? Because as we increase n, we're going to keep dividing by bigger numbers, so it's going to get smaller and smaller. And we know that the limit of that thing, 1 over n plus 1, is 0. So by the alt series test, the series converges at x equals -1. So now on our interval of convergence, we can add this equal sign confidently. We know it converges at x equals -1. Now we need to check at x equals 5. So let x equals 5. Then the series becomes the sum from 0 to infinity. And then that's 5 minus 2. So plug in 5 minus 2 to the n all over n plus 1 times 3n. So then that becomes, right, 5 minus 2 is just 3 to the n. And then we have n plus 1 times 3 to the n. And if we multiply by 3 to the n, divide by 3 to the n, that's going to cancel. So what's left is the n plus 1 in the denominator. Right, and so then what is this? Right, this is a pretty simple series, right? So we know that 1 over n plus 1, we know that that is smaller than 1 over n, right? Because we divide them by a bigger number. So therefore, compare to the series, the sum, the harmonic series, which we know diverges. Therefore, since so therefore that series, the sum from 0 to infinity of 1 over n plus 1 diverges. Right, so then we don't get to include the x equals 5. So therefore, our interval of convergence in the end just ends up being negative, right, this right here. -1 to 5 without including the 5, right? And our radius of convergence is 3. right? So just to make a point, let's copy this and bring it down. Okay, I just want to talk about one last little thing. I'm not sure if I did this in the last video, but right now when we look at our interval, right here the center of our series was 2, and then right we go 3 to the right, that's going to give us 5, and 3 to the left, because 3, remember, is our radius of convergence. So we go the radius to the right of the center and radius to the left of the center. That gives us -1. So this is our interval of convergence with a hole at 5 and then a filled in one at 1. Thank you.